My name is Elise Jennings. I work at the ALCF in the data science group. So first of two talks today, I'll be talking about uncertainty quantification and deep learning. So I know that you've just had a morning of machine learning and deep learning topics. I just wanted to get a sense of what people know already so I can move fast or move slowly depending. So who here is familiar with kind of Bayesian statistics, Bayesian inference? Okay, cool. Who here is currently doing anything in uncertainty quantification with deep learning or machine learning? That's interesting. A little bit? Okay. Okay, so that's really interesting, right? Because how many people here are actually doing machine learning, deep learning? Okay, so a good few people and not concerned about UQ. Or maybe who is concerned about UQ and wants to start doing it? Okay. So this is one of the real hot topics if we're talking now about doing scientific deep learning and scientific machine learning, right? We need error bars. That's what makes us scientists. So how do we start doing uncertainty quantification in deep learning and machine learning? That's going to be the topic today. So for those of you that already know Bayesian stuff, please bear with me, but I'm going to have to go through some of the basics for people who haven't heard it before. Okay. So neural networks are notoriously famous for being these black boxes, right? That we just kind of hit return and we don't know what's going on inside them. And so there's always this question of how do we know if the new model is making sensible predictions or it's just guessing at random, right? And we have people say, oh, well, if it generalizes, right? Well, what happens if it fails to generalize, right? Sometimes you're left just completely in the dark and then you go back and you say, well, I need to do hyperparameter searches. But ultimately, you're just guessing, right? It doesn't feel very scientific to do this type of analysis. So for this reason, people do criticize deep learning for its lack of transparency, its lack of interpretability, its lack of robustness, its lack of reliability. And I think those are pretty fair criticisms. So if we're doing any scientific analysis, understanding what the model's doing and why it fails, and putting some error bars on that model, or at least taking errors on the data and making sure that they're passed through the model, right? That we have some sense of statistical errors output is very, very important. Okay, so for those who may not have heard this morning, just a background on what a neural network is. So a neural network basically represents a function with many parameters, and it's just a recursive application of these linear functions followed by nonlinear functions. Okay, so we're basically curve fitting when we're doing deep learning. We just don't maybe want to admit it. And so I want to introduce this kind of notion of the neural network model as being something which can be probabilistic. Okay? So if we have this notation for our data set D, where we have our labels and our samples, X and Y, and then we have some parameters. So let's just call the parameters that we're fitting for theta here. So then our output or our estimation of the model is our Y hat here. And that's just the recursive application of those nonlinear and linear functions. And your network can be as complicated as you want. But ultimately, what you're doing is you're making a point estimate from this probability distribution here, right? The probability of your y given your x and your parameters that you've assumed, right? So now we are actually doing something where we can talk about Bayesian statistics, okay? So if you didn't think you were doing this before when you're doing deep learning, you're just getting a point estimate from that full probability distribution. Okay. So why should we consider using Bayesian methods in deep learning? Well, as I mentioned, there are many drawbacks to deep learning, right? So if you do this hyperparameter fitting, which we all do, there are many of those. They require specific tuning, and it takes large data sets or a huge amount of time and compute in order to find those specific hyperparameters. And that can feel a little unsatisfactory that we're just doing some random searches or grid searches for parameters, and we don't really understand why the best ones are the best ones. The second point is that the neural network trained with the best hyperparameters is still a point estimate, right? Of all the possible models that are out there. And you should account for uncertainty for all the possible models, or maybe you're in some pseudo-minimum of the parameter space. So there's no uncertainty in these point estimates, and this can be very important when we think about the outputs from these deep learning models when they're doing something pretty serious. They're doing things like medical diagnosis, or they're predicting things in financial markets, or they're operating self-driving cars. We definitely want error bars on what the model's predicting here. And then it's very common to just use very large neural networks and fit the data set and use regularization to prevent overfitting. And so in order to do this, we do need efficient search algorithms or guesswork to find the best network architecture. So in the traditional sense, it can be very difficult then to explain when your deep neural network fails. Okay, so everyone talks about, well, I do get probabilities out, right? I get my softmax. And if there's one thing you want to take away from today is softmax does not tell you about the uncertainty in your model. It is not a statistical and it is not a systematic measure of uncertainty. Right? Your softmax just gives the probabilities for each class given your assumption of a fixed model. Okay. It's no uncertainty in the model, and you're not talking about uncertainty in the data either. So there's a couple of very famous examples that you can point at. So deep neural networks can be easily fooled. So in this paper, they actually just generated these garbage images on a network which was very high accuracy in training and generalized very well. And then they showed underneath what the network guesses. So the network thinks that this is a king penguin, it thinks this is a starfish, it thinks this is a baseball, with very high certainties, right? Softmax certainties. Another example I really like is this CFAR10 data set, which we all use, right? And we get our students to use. Take your CFAR10 data set, right? And there are no green apples in the CFAR10 data set, right? There's just green frogs. And then use it on the CFAR100 data set. And it will tell you with probability, your softmax probability of 0.9, that all these images are green frogs. Okay. So it is really easy to fool these things, right? And so it's always good to keep in mind what that softmax means. Okay, so what are Bayesian neural networks? So you could think of training the network as an inference problem in which we solve Bayes' theorem. So if you're not familiar with Bayes' theorem, it's the probability of some parameters in a model given the data set, right? So this is your posterior distribution for those parameters given the data set. And we evaluate this with our likelihood evaluation, right? So the likelihood is the probability of the data given the parameters in the model. So there's an assumed model in here when you see the theta, times some priors on those parameters, theta, divided by the probability of the data itself. Okay, so we can just look at the numerator for the moment here. So this is what we mean sometimes where we're saying, well, we want to maximize that likelihood for the parameters given the data, right? So probability of the data given those parameters. We're going around in parameter space trying to find the optimal model and parameters given some prior information, right? Move away from the prior and find the posterior distribution. Okay, so the network, you can think about this as doing something similar. So a Bayesian neural network is just a neural network where now there are distributions over all of the weights. Okay, so initially in a standard neural network, you initialize all those weights and biases randomly, and then they're just point estimates from now on. Okay. Now you can think about a Bayesian neural network is at each point, at each node in the network, instead of just having one fixed number, you have full distributions that you're modeling at each stage, and these distributions can evolve away from their priors over time. Okay. So what we get out is not just point estimates of our y hat. What we get out is a full distribution for y hat. Okay. And then we find a weighted average over all these parameters, which can be thought of as an infinite ensemble of neural networks. Okay. So now, in theory, you no longer even need to do hyperparameter searches on your architecture because you're automatically marginalizing over those parameters. And there's some really nice work, Neil, first in 1995, and then some subsequent papers, where they showed, mathematically, that a single layer, infinitely wide neural network with distributions over the weights is equal to a Gaussian process. So now we're back on very familiar, very solid statistical ground, right, where we understand what's going on if people work with Gaussian processes. We've done this for decades, and it's a pretty robust, trusted method, right? So you can just say to people, well, if you distrust neural networks, you can just say to them an infinitely wide neural network is a Gaussian process. So when we don't do an infinitely wide one, we're just making an approximation to a Gaussian process. Okay, so in pictures, this is what it looks like. So now at each step through the network, your weights are being sampled from some distribution. Yeah?
So infinitely wide means infinite amount of layers, or?
No, so that in that case, they showed that a single layer infinitely wide, so single layer.
Okay, so wide isn't, yeah. Okay.
Yeah. Yeah. So in the limit, right, of infinity, then it's a Gaussian process. Yeah. Okay, so with your Bayesian neural network now, right, for each of these weights, you have a prior distribution, which is actually being evolved. So it's the distribution which is being fit for at each stage. So in the beginning, you can assume whatever you like for those distributions, right? We pick a Gaussian because it's what we're familiar with. We assume something for the mean and standard deviation there. And then as we evolve our network, the actual distribution itself evolves away from that towards the optimal configuration. And now the prediction here, right, the probability for our y hat given our data set and given our model is actually an integral over all those parameters that we assumed, right? So now this takes care of hyperparameter optimization for us because we're marginalizing over all of those possible parameters that we could have chosen, all of those possible network structures we could have chosen, right? And so how do we do this, right? So now there are actually many inference methods which allow us to approximately solve for this posterior distribution. So these networks can be really big to start off with, right? So now you're not just following weights and biases, you're following full distributions for each of these. You're sampling from full distributions at every single stage, right? You're still doing a forward and backward pass through the network to update this. So now you need a different method to do this. And they're very... There's lots and lots of different inference methods now. So this was kind of a seminal paper which came out because people thought, well, you just can't do this at scale, right? It's just not possible computationally. And so this paper by Graves showed a practical variational inference method which allows us to do this at scale and find that posterior distribution with this variation. So this is just an output of the different classes for doing variational inference from TensorFlow probability. Some of them are kind of familiar, like MCMC methods or Gibbs sampling, but it's the variational inference one that most people are using now who are doing Bayesian learning. Okay, so as I mentioned in this Bayesian approach, you automatically marginalize over your hyperparameters. So in theory, you do not have to worry about that anymore. They are taken care of. So this was actually laid out in a paper by McKay, which I recommend. It's kind of the first time it was laid out, a practical Bayesian inference for backpropagation networks, and it's a pretty nice read because it was the first time anyone had pointed out that this could be done. So it naturally accounts for uncertainty, right? Because you end up with that full posterior distribution for your predictions, you have everything, right? You can have 1 or 2 sigma confidence intervals, you can make all those nice plots. It's more robust to overfitting, as now you're getting some notion of an average with error bars rather than just a point estimate from a distribution in a fixed model, right, which could be incorrect. Now the notion of L1 and L2 regularization, right? Whereas if you ask someone, why do you do L1 and L2 regularization, they would always say to prevent overfitting, right? But that's not really an answer. Like, why the square, right? Why the form of L1 and L2, right? Now this actually puts a framework in it. L1 and L2 are actually prior choice for the weights, right? You can actually relate them back to continuous distributions. And we can also do things like model comparison with Bayesian evidence if you do want to play around with the network or try fundamentally different connections in the network. Okay, but then the big question that people always had about this since McKay's paper was, well, how well do they scale? Can we do this at a large scale? Yeah.
Sorry if it's very basic, but
No.
what is L1 and L2?
Yeah, so they're basically regularization terms which are added onto the loss function. Okay, so you can think about L1 as being here in this Bayesian sense, it's a choice of prior with which is the Poisson distribution. And for L2, it's actually a choice of prior of a Gaussian distribution. Right? And so you can see that mathematically now if you start to think about it. But previously, right, if you ask most people, they don't know why they're doing it really. They just say to prevent overfitting, but that's not really an answer. Right? Why not the cube? Why not why the exact mathematical form of L1 and L2?
I have a question.
Yeah.
So what kind of computational power do you need for this?
Yeah, so I'm going to go on. That's exactly my bubble here, right? So how well do they scale?
Maybe that's also in the application atrophy.
Yeah. So right now, you can do this on your laptop. Yeah, with these new variational inference methods, it's possible to do this. So we should be doing it. And in terms of how much longer does it take compared to a standard neural network, it doesn't take that much longer. The key thing is that the time to solution, right? The time taken to get to the same level of accuracy does take a little bit longer.
Because typically, uncertainty quantification takes a lot of computational power.
Right. So as I said, to actually do a forward and backward pass through the network right now with the variational inference techniques, which are in the code I'm going to talk about, it doesn't take that much longer. But to get to the same level of accuracy takes a little bit longer. But I think it's definitely worth it because now you have error bars on your model.
Do you need an assumption on how well the neural network should do in order to categorize these stereo distributions?
Sorry, could you repeat that?
Do you need any assumption on how well the neural network do in order to categorize the posterior distribution?
So the neural network now is the thing you're using to find the posterior distribution.
But I guess I'm not understanding is that, like you can make like a very bad neural network. To me, like the bad models are way more than the good models.
So right now, right, in a traditional neural network, you have all these choices of network architecture, right? And you choose, as the practitioner, you choose which one and you run it. And as you say, you could choose a bad one, right? In a Bayesian world, when you run a Bayesian neural network, that network is automatically sampling from that space. You are no longer doing that choice.
But then the output is like, a distribution that's not very meaningful because...
So no, it's marginalizing over that space. So it automatically will know that it's taken a bad choice, right? Because it's doing variational inference to get towards a posterior distribution, right? Make sense? Okay. So there's actually lots of codes out there now which you can use for doing this Bayesian deep learning. So there's PyMC3, there's Stan. Some of the drawbacks are, I think it's been updated recently, but it can be slow in higher dimensions. The big ones was first developed was Edward by Justin Tran, who then later joined Google. And so now this has been joined TensorFlow, and this has later been put into TensorFlow's TensorFlow probability. So it's actually an upgrade to Edward called Edward 2, which is being used in TensorFlow probability. There's the SK Pro machine learning toolbox, Pomegranate, and several others, right? So these codes are out there, they're being developed, and you can run them on your laptop or at our supercomputers, right? You can run it on Theta today. Yeah. Okay. So I also want to mention something else people may have heard about, which is Dropout, using Dropout to get uncertainty quantification. And this is something which you can definitely do as well. And in theory, it's identical to doing Bayesian neural networks. But it is a cheap and dirty method, right? Because unless you implement it exactly, it's not going to be the same as a Bayesian neural network. So with Dropout, you have this notion of a fully connected network, but with Dropout, there's a probability P to drop the weights from the network at training time, right? So you just zero out some of those nodes. And the idea here is that you're preventing co-adapting of the nodes, right? Codependence on those nodes, right? So that it generalizes better. That's the idea. And so how does the expression here change for your estimation of the model? Well, now for these nodes that you're dropping, you sample from a Bernoulli distribution, a 1 or 0 maybe, to drop the node or not at runtime. And then you can just think about these as extra bias terms or weights terms, which we need to tune. Okay? But again, you need to choose that dropout probability. And only in very particular cases is this going to be equivalent to a Bayesian neural network, right? So the dropout network is also a Gaussian process approximation in the same way that the Bayesian neural network is. And there have been some studies in terms of, well, what are those optimal dropout rates? And one interesting paper found, for the input layers, a probability of 0.8 makes sense, whereas for hidden layers, 0.5. And this makes sense because for the very first layer, right, you want to maintain as most of the information from your samples going into the network as possible, right? And then reduce codependence of the hidden units in the network as you move forward. Okay. So how does Dropout compare to Bayesian neural networks? So Dropout can be interpreted as averaging many models with shared weights. Okay. But in the Dropout model, each of those models is equally weighted, right? Which is not the correct assumption. Whereas in a Bayesian neural network, it's the proper way of averaging over all of those distributions. Okay, so you're still limiting, your uncertainty quantification is still slightly unrealistic in a Dropout network. Using Dropout, though, has big advantages. It's much, much faster than the Bayesian neural network. Okay, that's why a lot of people do it. And in a sense, you also don't have to tune some hyperparameters there, right? So, and like we said, the Bayesian neural network can be slow to train and difficult to scale, but you're marginalizing over your hyperparameters. Okay, so I want to show just a quick example. So everyone's familiar with this MNIST data set of handwritten digits. So we can just play around with this. So for this example, I'm using TensorFlow probability. So let's just take one of these examples, right? One of these digits. So is this a 3 or a 5? So for me, this isn't clear, right? And I would hope that my network would be uncertain as well. So if I run this with something like TensorFlow probability, I just wanted to show you, this is just a standard convolutional neural net where you can make each of the convolutional layers and each of the fully connected layers Bayesian, right? So now you're sampling from probability distributions. And what you get out as the network is learning are no longer point estimates. They're these full distributions, right? So this is at an early iteration in the network. These are the posterior distributions for the probability of it to be that digit given the input. Okay, so given this input image, these are the probability distributions. So you can see it's not quite certain, right? At the moment, something looking like it's a 6. It's not quite clear. This is early in training. Then as it's converged, this is at iteration 6,000, you can see that for each of the other digits, apart from 3 and 5, it's peaked around 0. But then for 3 and 5, you see this nice distribution of uncertainty, right? So this definitely coincides with our own intuition about this image. So just to zoom in on those two, so this is what you get out of a Bayesian neural network now, right? You get out the probability of it being 3 given the input and the assumed model that you worked with. Okay, 3 and 5. And then we can do this for other digits and play around with this. It's kind of fun. One of the other things you can output is, well, what do the actual distributions look like for the weights and the weight means and the standard deviations, right? So you can't actually, it wouldn't be worthwhile to look at all the distributions for all the weights. So we just summarize it in terms of the distribution for the weight means and standard deviations at an early iteration and then as it evolves. And you can see in this example that the actual mean doesn't change that much away from the prior, but for the standard deviation it does. For the exact same image, if we were to just use a standard neural network and look at the softmax outputs, it would tell us with probability 1 that this image was a 5. Right? So you don't see that uncertainty there between it being a 3 or a 5. Okay, so I just want to drill that home. Softmax is not telling you anything about statistical or model uncertainty. Okay, so I do have a couple of notebooks that I was hoping people could work through if they're interested. So I'll end the presentation here, and then we'll go to the notebooks. And then if people have questions, you can just let me know as you're working on the notebooks. Yeah.
So for this example, we can see that it has nice distributions for the 3 or 5. I was wondering, like at the beginning of the presentation, you said the model was trained on green frogs.
Yeah.
You showed green apples except for all green frogs. What sort of uncertainty would we see using this Bayesian approach?
Right, so you definitely wouldn't see that P of 0.9, right, with a Bayesian network. One of the things you can do, if you're certain that the class or the data set you're training on is not fully representative, one of the things is always a good idea to do is to have, for example, for classification, have a class of unknown, right? And then in a Bayesian sense, it will show some high probability for it to be the unknown class, right? So that's always a good practice there. But you will just basically see very low probability distributions, right? You will not see something like a delta function peaked at 0.9, right? And that will indicate to you that it doesn't know what those green apples are. Yeah. But I think it's always a good idea to, if you're doing classification, to include that class of unknown, right? Because then it allows for your data set to be biased, which it probably is in some way. Yeah.
So in uncertainty quantification, sometimes you have error or uncertainty propagation. How does that fit into it?
So there's a couple of ways. I mean, so are you talking about statistical or systematic here?
Well, if you have like an input and output, then you have some error involved, and then you feed that into the next.
So are you talking about error on the samples input into the network and how that propagates through the network, or okay? So the reason I was asking is that you could also think about propagation of the uncertainty with multiple calls to the network, right? How does that propagate through? So with the Bayesian neural network, you can actually measure. I mean, what I'm calling this error is a statistical error, right? So if you have a delta x, how do you propagate that through to a delta y? And so with your posterior distribution, that you're actually using the network to fit for the posterior distribution, okay? And so there are parameters, hyperparameters in that posterior distribution. So let's say it's a Gaussian, or we assume it's a Gaussian in the beginning. Then we're fitting for the mean and standard deviation there, okay? And so the standard deviation is our delta y, right? And so if we have some understanding on how delta x, if we have some functional form, or we can assume some functional form there, then we can have the network fit for that delta y. And in a sense, then we have allowed the delta x to propagate through the network and give us a delta y. Does that make sense? But that delta y is made up of both the uncertainty in the data set x and the uncertainty from the model there, right? So there's two sources of uncertainty. Yeah.
So I just want to make sure I'm understanding this right. I mean, you said during your talk that the Bayesian treatment here samples or marginalizes over like the network structure itself.
Right.
So it's not clear to me how you can do that in like a well-developed way, because like network structure is seems like an incredibly like ill-constrained concept. I mean, you can have in principle, even if you're just looking at multi-layer perceptrons, you can have an infinite number of, you can have infinite depth and an infinite width, and
Right.
like I don't really know how you would construct like a well-behaved prior on that.
Right. So you can think about at a single point in a normal neural network, right? It's just a point estimate of the weight there, right? And now you have a layer with a certain number of nodes, and they're all just point estimates of the weight, right? So you could reconstruct that, right? To think about, instead of having those point estimates, right? Those discrete point estimates at a single layer, right? Now I'm sampling from a distribution as an approximation to that, right? Because now you have a continuous distribution. I mean, it's identical, right? So you either have, let's say we have a single layer network with 10 neurons. At every point, you randomly initialize those weights, right? Randomly initializing those weights actually means you're sampling from a distribution and you're sampling 10 random variables, right? So maybe you use TensorFlow. TensorFlow is doing this for you. Do you even know what distribution it's sampling from? Yeah, so it's probably sampling from a uniform distribution, right? So right now with Bayesian learning, we can take control over that, right? So we could then say, well, that's equivalent to a single node where I sample from a distribution, but I do that maybe 10 times at a single node. That distribution I'm sampling from is still a continuous distribution, right? But now I get to choose. I get to say it's a distribution which is Bayesian in the beginning, and then I allow the network to distort that distribution away from that towards an optimal distribution, right? Does that make sense?
Kind of, yeah.
So in a standard neural network, you have these discrete points, right? Right. But in the Bayesian neural network, you're actually sampling from continuous distributions. Okay.
But the number of samples you take is that also marginalized over?
So it's not representative. So you can think about the forward and backward passes through the network, right? You're sampling from the distribution. But that distribution is still infinite. So you still have exactly the same probability. Like you have far more resources available there than in the discrete network with just 10 neurons. At each stage in the discrete network with 10 neurons, there are 10 points which are being estimated there, right? In the Bayesian neural network, I'm choosing from an infinite distribution. Right. Yeah.
Good question. What's on the x-axis in the distribution plot? Perhaps you can go back 3 or 4 slides. No,
Yeah.
not this one. One more. Yeah, here. What's the x-axis?
So I think. I'm trying to remember.
So we have a distribution, right?
Yeah.
I was kind of confused about that.
Oh, so I think I put the distribution of softmax probabilities on the bottom here. So it's a concatenation just for that prediction of that number, right? So it's probabilities and probabilities there that I'm producing. I wanted to show a little bit of the notebook just for people who are interested. So for the notebooks, you can run it in Colab. It might be the easiest way to do it. Okay, so I added 2 notebooks, just kind of summarizing what we can do with the TensorFlow probability package. I just think in the time that we had, there wouldn't have been enough time to show you a full implementation. So it's definitely up to you guys if you're interested. You know, you can play around with these notebooks, and it just gives you a very basic sense of what we can do now with TensorFlow probability. So basically now you can do all these tensor operations on probability distribution functions, and they have lots of distribution functions which you can play around with here.
Is this the same, can we get there from the same GitHub on the earlier presentation?
Yeah, so it should be under the title Bayesian Learning, Uncertainty Quantification and Bayesian Learning, if you see it there. There's two notebooks. The first is the Introduction to Probabilistic Learning. So in this one I'm just showing you here, so what we've done some import of TensorFlow probability and the distribution class as TFD here. And so you can do things like, okay, well, I want a normal distribution with some mean and some standard deviation, and then we can sample from it and we can do some plots. Okay, so that's kind of, we can do that with lots of packages, but the nice thing here now is that you can actually do distributions with different shapes, right? So now you can have tensors. So here we can create a batch of 3 normals. And so this broadcasts, so here each of the normal distributions, these are the means for them, and then this is what's broadcast for the standard deviation. And then you can sample from each of these. So when you say normals.sample, you're actually taking samples from 3 independent normal distributions. Okay? And then when you ask for the log probability of these 3 numbers, it just broadcasts, so you're actually sampling from 3 different normal distributions. Does that make sense? And so then we can just play around with looking what they've done. And they also do have multivariate normal. So you can see now how this is, so in TensorFlow probability, actually constructing the network, all of this is hidden from you, but this is what's going on underneath, right? They're sampling from this. So maybe I'll show you. So in this notebook, I have some example using Gaussian processes with the TensorFlow probability and how you can sample from this and use it to fit data for people who are interested in Gaussian process work. If you wanted to see an example with a neural network, it's in the other notebook called Probabilistic Layers with Regression. Okay. And so in this example, I walk you through different levels of uncertainty. So here we generate some data set. So the blue points here are the data set. And let me see. This is the model that I have here. So in the very first instance, there's no uncertainty. So I just have a dense layer here. And then for the next part, I have a distribution function where I'm just fitting for the mean and drawing from a normal distribution for the standard deviation. Okay? But because this layer here is non-probabilistic, the mean is completely deterministic. So there's no uncertainty in this first cell here, right? And so this is what we get out from a kind of standard neural network. Right? These are the data sets, and this is the mean of the model that it would predict. Okay. So the next thing we can do is, well, why don't I make the standard deviation here something that I fit for? So this is this notion of statistical uncertainty, right? So I'm saying, I think that the delta y of my model has some dependence on the delta x, right? There's clearly a scatter of the values x around the model y. So how do I incorporate that into my model? Well, here, now I'm no longer fitting just for the mean, I'm also fitting for the standard deviation. So in the second to last layer, I need to output 2 variables here from the dense layer. And now what we get out from this, semi-Bayesian neural network is we get out these standard deviation error bars, right? So we're still getting a posterior distribution. It's no longer a point estimate, and now we have these error bars on our data. And then how do we incorporate model uncertainty, right? So now what we need to do is we need to actually go ahead and change the model itself. So this is the important part here. Now we've changed the second to last layer to be dense variational. And now each of those weights is actually a distribution which we're drawing from with some mean and some standard deviation and some Kale terms. So I know this is a lot to throw at people, so I just wanted to give you these notebooks and you can look at them and play around with them if you want. Once we change the network, now we can get some sense of, well, what if my model changes, right? And like you asked, this is in effect, what if my network changes? Now you're actually seeing different models, right? Different predictions for what that y is.
So on the back end, is this doing some sort of like abstract function composition, or is it like resampling?
Or is it
Like resampling or something like that?
so for which stage?
Just, you know, like computationally when you're training it, what is it sort
So
of?
are you familiar with variational inference? Okay, so in the beginning, right, variational inference is a technique where you basically assume, you guess any distribution, and then that distribution is evolved using, it's still doing a stochastic gradient descent, but now it's a distribution which is being evolved away from that in order to minimize some alternative loss function. The loss function is no longer something which is like, you know, the mean squared error loss function, right? Now your loss function is actually goes back to the Bayesian framework, right? And your loss function now is a log likelihood term plus this Kullback-Leibniz term, the KL term, right? So mathematically, it's a restructuring of that loss function, which is being minimized at each step, because now we're dealing with distributions rather than point estimates.
Right. Maybe how does it parameterize these distributions?
Well, how you parameterize any distribution. It depends on the distribution you choose, right? So if you choose a normal distribution, then the normal distribution is completely described by a mean and variance.
Okay, and so then you specify it's normal and then it's stuck being normal, it doesn't evolve away from there?
No. So this entire technique, the variational inference, it's the notion of assuming a prior, but in the method you evolve away from your prior towards your posterior distribution. If it doesn't evolve away from the prior, then you've just done something wrong. But that's true in any method like MCMC. Right, so that's the variational inference. You're varying the prior. The prior shouldn't have any impact on your results. The prior just introduces prior knowledge, so you start off in a reasonable point in parameter space. Yeah.
So speaking of your choice of prior, I guess sometimes if you only have a finite number of observations, your prior could bias you. So do you have suggestions for how we should choose that prior? Is Gaussian generally good? Or?
So here the prior choice is nothing to do with the number of samples, right? The prior choice here is your choice for the prior for the weights and the biases, right? So it really shouldn't matter. So you could think about, well, what if I want to introduce domain knowledge into the network, right? What if I know that, you know, certain part of the network is doing some feature identification, right? Feature extraction. Then you can impose some kind of physical priors on that part of the network, right? You can think about it like that. Or if you know, well, I know the network, this node, right, ultimately is outputting something which should not be non-zero, right? Some very physical constraint like that. Then you can constrain that node that way, right, with the prior information. But ultimately, when you're running these networks, you need to always check, right, like just output what the prior distribution was and what your posterior distribution is that you get for each of those weights, and make sure that they're not the same. Now, I have seen examples where there are certain points in the network where it doesn't evolve away from the posterior or from the prior distribution, or it doesn't evolve, it evolves towards almost a delta function, right? And these are very interesting points because it means that that node in the network doesn't actually need to be probabilistic. It can be deterministic. And those are kind of interesting points in the network.
So that's not a sign of failure, that's actually
No.
a sign that you didn't.
It's a sign of the network deciding what is the most efficient thing to minimize that loss. Yeah. Okay. Okay, so I'm going to move on to the next topic, if that's okay, Martha.